So in our previous video, we were looking at problem 2 from the 2014 exam, and in that video we looked at part A of this question. We now move on to look at part B. Part B tells us that the region that was defined previously, which is given in this diagram down here, the region R is the base of a solid, and for this solid, each cross-section which is perpendicular to the x-axis is an isosceles right triangle with one leg in the region R. And we're asked to find the volume of the solid. You'll recall in the previous question that we had already defined our curve as f at x, and our line we knew was y equals 4. That's already been defined, and as well, in the last question, we set the curve equal to the line in the calculator and discovered that those two intersect at x equals 2.3, and we defined that as a. So that's already been done, and so we can move straight into this question now, and the next thing we need to do is take a diagram and try and identify what the slice looks like. So we imagine slicing down perpendicular to the x-axis and extending this out into 3 dimensions. So this is going to come out something like that. This will be a 90-degree angle. And if we try and give this some thickness, we imagine this coming out of the board. It's going to come out something like that and like that. And we can sort of imagine this now in 3 dimensions, the triangle coming straight out of the board at us. So that I've got that distance, which I'm going to call B, or this distance, which is also B. So now, what I want to do is take this slice out, and I'm going to identify that as dV, and I want to draw this as if I'm looking straight down at it. So, looking straight down on this, I'm going to see an isosceles triangle. I've already labeled this as B, and because it's isosceles, that's also B. And I want to know what the volume of this slice is. The volume of the slice, of course, is going to be the area of the slice times its thickness. And the area of the slice is a half base times height, which in this case is a half base squared. The thickness of the slice is dx, coming into the board. So the volume of my slice is 1/2 b squared dx, and the volume of the whole solid is just going to be the sum of the volumes of those slices. And the way we sum an infinite number of slices is through this process of integration. So I have the volume is going to equal the integral from 0 to a, because that's where my x's are running, of 1/2 b squared dx. The only problem left is to identify what b is. We know that this is a dx, and so we know that this has to be a function of x. So we have to write b in terms of x. So I can come back up to the diagram, and I can see here that in order to find the length of this base, I need to know 2 things. I need to know what is the height of the triangle and what is the height to the bottom of the triangle. If I look at this, I recognize that there are 2 separate heights that I have to deal with. To the top of the triangle, that distance is always going to be the same, and that's going to be 4. And we can see that as we move through, as our slice here moves through this region, the top of the triangle never changes. The bottom of the triangle, however, is going to be changing with the curve. And the height, the distance from the x-axis up to the bottom of the triangle, this distance is going to be my function, f. And so it's pretty clear, looking at that the distance that we want, our distance b, must be this distance, which is 4, minus this distance, which is f. So this must be 4 minus f. So now I know that b is equal to 4 minus my function, and I can put that straight into my expression. So I now have the 1/2 here is a constant. I'm going to pull it out in front of the integral. I'm integrating from 0 to a still. B I've now defined as 4 minus f at x, quantity squared because the b is squared, times dx. In the previous question, I had already put f at x into my calculator and a into my calculator. If we go back and look, we can see that they're still there. Okay, this quartic function was defined as f. We solved f equals 4, and we got this value of 2.3, and then we put that value of 2.3 into the calculator and stored it as a. So that's already been done, which means that I can type this expression exactly the way it's written here into the calculator. And when I do that, the calculator gives me an answer of 3.574, which is the volume of the solid that we're asked for in part B.